Hello everybody, I'm Mark Tewksbury, your host for this program. Our goal is to reveal the methods and materials that turn out the products we see around us every day. If you think you know everything about these things, you're in for a surprise. There's a whole world waiting for us to discover here on How It's Made. The topics today, nails and staples, safety glasses, fabrics, and bicycles. Toothpaste wasn't created yesterday. Thousands of years ago, Egyptians made theirs with pulverized pumice stone and wine vinegar. Happily, they've improved the formula. Today, there are still abrasives, but now it's water with added sweeteners, detergents, bicarbonate of soda for whitening, and delicious flavors. For connecting wood to wood, there's a great variety of fasteners. You can use common nails, spiral, finishing, even staples. See? We've got it all nailed down for you. There are hundreds of varieties of nails being made, and they're made of very durable carbon steel, all starting from steel wire. Rolled up on a drum, this steel wire weighs in at 2,045 kilos. The wire's diameter is 6 millimeters, and that's too large, so they'll have to reduce its size. Using many drums, they're going to pull the wire successively to gradually thin it. Then they'll roll it up again. When full, this roll will contain 23,500 meters of wire weighing 1,136 kilos. The wire now has a diameter of 2.84 millimeters, so it will have to be reduced by half. Now they're going to cut the wire into little rods. The cut rods are gathered up with this electromagnet and dumped into a machine that will process them. Here the rods are made into nails. The metal rods move along slowly and a blade forms the nail points. These blades are changed every 600 hours. This machine forms nail heads by flattening them with great pressure on the rod ends. Nail heads are formed at a rate of 1,400 per minute. The manufacturing of nails is now finished. They fall into a chute, then into this collecting bin. Nails are sold by the pound or embedded in plastic rolls, as we see here. This machine inserts 167 nails into each roll. The plastic strip has teeth, and the nails hook into these. They handle the rolls with gloves, since the coating applied to the nails is not yet dry. This machine produces 5 rolls a minute for a total of 835 nails. Making spiral nails requires an extra processing step. This machine puts the spiral into the nails with these cylinders and welds them. It makes 1,200 nails a minute. Then the nails are put together into strips for use in pneumatic nailing guns. Each strip contains 30 spiral nails. To help them stay in place, the nails are coated with a resin that dries in 4 minutes. This is the nailing device that uses nails on a strip. It sets the nails in one strike with the user's trigger finger. Now, we move on to the fabrication of staples. The staple press binds 80 iron wires which have been well lined up. The 80 small wires are placed side by side. The wires are glued together. Then the wires come out well adhered to one another. The staple strips are fed into this machine. It cuts the staples to the desired length and folds them in one stroke of this press, which applies 40 tons of pressure. Staples are formed on this gauge, and the staple strips are then ready for packaging. Every day, they produce a total of some 25 million nails here, which require the processing of 10,000 tons of metal annually. Things as diverse as using a drill or entering a small court to play racquetball can be hazardous to your vision. There's a simple way to protect your eyesight: with safety glasses. Many sports and trades require the wearing of safety glasses. These glasses are made by plastic molding. Here we see the interior of a mold. The optical part of the lens is mirrored in order to be as transparent as possible without being deformed. The glasses are made by melting the primary material, a plastic resin called polycarbonate. The resin granules are poured into this machine. It becomes liquefied at a temperature of 250 degrees centigrade. The liquid plastic is injected into the mold under pressure over a 30 to 60 second period. The plastic hardens rapidly, and the glasses are then removed from the mold. They mold several glasses at a time. The glasses are separated by hand and then are given an initial visual inspection. The glasses are placed on this support. They're then taken to the laboratory where they'll be given a surface treatment. But before beginning the treatment, they're washed to eliminate any impurities and to assure that the coating treatment adheres well to the lens. When they've been washed, the glasses are then rinsed in clear water. The glasses are now gently soaked in a chemical solution which prevents misting and scratching of the lens. This coating now has to be cooked. They direct the glasses towards an oven heated to 120 degrees centigrade. The soaking and cooking processes vary between 30 minutes and 2 hours. Each pair of glasses is inspected to make sure there are no imperfections or distortions in the lenses. Then the glasses are placed on this support. This milling machine automatically removes the last piece of polycarbonate. This one was left in place so that they could be able to handle the glasses without having to touch the lenses. At this stage of the production of the glasses, the nose piece is glued on. Certain pairs of glasses are selected from each production run. Here they evaluate the resistance of glasses to a racquetball hurled at them at 140 kilometers per hour. Here a hockey visor is tested against a puck traveling at 100 kilometers an hour. To conform to safety standards, the glasses must withstand these tests. It confirms that they're truly safe. They now proceed to final assembly steps in making the glasses. The last few pieces of the glasses, such as the plastic ear stems, are installed. Now completed, the glasses are placed in cases. It's the final step in their fabrication. They make several types of safety glasses here: industrial, hockey and football visors, swimming goggles, racquetball glasses, and for other uses. This particular facility can turn out thousands of safety glasses every day. And the polycarbonate resin used to make those safety glasses could very well save your eyes one day. Weaving mills make literally zillions of fabrics in every conceivable pattern and color. Great, but choosing exactly the right one, that requires some patience and perseverance. Fabric is made from thousands of braided threads. This mill has 700 bobbins of polyester. Each bobbin contains 250,000 meters of thread. We begin by separating the threads. This warp unit takes the 700 strands and assembles them. Then this comb separates them. Other strands are added, and in total, there will be 7,000 of them well aligned. One fabric is composed of threads braided at 90 degrees. The warp threads are assembled lengthwise, while the weft threads are joined transversely. To prevent the threads from tearing, they pass through a bin of glue. These rollers eliminate the surplus. The glue will be removed with water before dyeing the threads. The glued together threads exit this machine. These large green cylinders are heated and dry the glue on the threads. Knitting will soon begin. The 700 strands are newly separated on this loom roller. Each thread must pass through a blade to produce a specific design. This machine takes the 7,000 strands of thread one by one, and they pass through the blade. It's a highly precise operation. The threads pass through a blade, and the weaving finally begins. On this Jacquard-type loom roller, the warp thread is inserted by a jet of air. The weaving machine assembles 2 loom rollers made of 7,000 strands. The fabric reaches a width of 3.65 meters. The dark threads are inserted into the weave. They insert 600 weft strands per minute. The blades remove the weft strands to insert the warp ones between the two. A comb pushes the weft. The plate of the breakage chain stops the machine should a thread break. This bobbin contains 250,000 meters of thread. That's 250 kilometers. The weft thread is in the insertion nozzle. When a weft is inserted, an air jet nudges it in. The loom roller operates at full tilt. It makes 600 thread intersections a minute. Weaving is now over. We move on to the following steps: washing and dyeing. Washing is done in a soapy solution at 80 degrees in a continuous manner at a speed of 60 meters of fabric a minute. The fabric is rinsed in clear water of about 30 degrees. Now it's on to dyeing. This is done with jets. Up to 12,000 meters of fabric are placed in clean water into which colorants have been added. The solution is heated and the fabric soaks here for about 6 hours. Then it will be rinsed in lukewarm water. The fabric is placed in a bin. This machine is called an opener. It unfolds and stretches the material before rolling it up on an immense roller. And now the roll is almost full. We now move to thermosetting in a high-temperature oven which dries the fabric. The temperature is 200 degrees centigrade at the oven's entrance. The fabric circulates here for 45 seconds. This finished roll weighs 1,500 kilos. The bobbin that we saw at the beginning has produced 25 kilometers of fabric. Multiple gears, light but solid construction. From rugged mountain paths to quiet city trails, bicycles are built better and perhaps more popular today than ever before. A French invention of 1790, the first bicycle resembled a two-wheeled wooden horse without pedals or handlebars. In 1817, a German gave it direction control. The addition of pedals to the front wheels came from France in 1861. The British contributed as well, adding the large front wheel in 1870. By 1903, all countries participated in the first bicycle Tour de France. A bicycle is a beautiful piece of engineering. The frames are made of steel or a chromium molybdenum alloy known as chromalloy. Fabrication begins with these hollow tubes. The tube cutter cuts the steel before sending it to the bender. The bender curves the tubes cold, exerting strong pressure against the bending jig. The tubes must now be machined, that is, cut into lengths so that they correctly fit into one another. During this operation, cutting oil cools the tube. The tube is cut, taking into consideration the insertion angle of the other pieces. Tubes to be welded together are placed in this support. They insert a piece in an alloy of silver and bronze, which increases the strength and produces a better finish at the welding point. Welding now takes place. Welding of the frame requires about 2 minutes at a temperature of 800 degrees centigrade. Once welded, the part takes 4 minutes to cool. They proceed in the same way with all the tubes which form the frame of the bicycle. At this stage, it's important to straighten the frame, which could have deformed during welding. They verify the alignment of the tubes and they straighten it out cold with a tool that sets it to the right dimensions. Now they're going to paint the frames. Paint is applied with a spray gun and adheres to the frame by static contact. Then the paint will be baked in a natural gas oven at 218 degrees for 15 minutes. The frame is now cooled and we can begin the assembly. The labels are now applied. In another department, an employee assembles the handlebars. He installs the mechanism for the brakes and the gears. Now we move on to the wheel rims. The 36 stainless steel spokes of each aluminum wheel are installed manually. The dexterity of these workers allows them to install spokes on 65 wheel rims in an hour. This spoke tool allows them to screw the spokes into the rim. This machine exerts a pressure on the spokes so that they'll have the desired tension. If there's too much or not enough tension, the rim will be crooked. This machine aligns the rims, essential for proper functioning of the bicycle. It automatically adjusts the spokes so that the wheel will be truly straight. Next step, placing of the tubes and the tires on the wheel rims. Set upside down, the bicycle circulates from one workshop to another where they will install the last mechanical parts. These accessories are not made here. The handlebars, the pedals, the fork, the brake, and chain mechanisms are all installed manually. Here they screw on the rear brake plate. Finally, they inspect each bicycle to make sure that the bolts are well tightened and that everything's working properly. Then it's on to packaging. This factory makes 2,500 bicycles each day, assembled from various tubes of chromalloy. Each one weighs about 11.4 kilos and will run for thousands of kilometers. A picture's worth 1,000 words. I hope what we've shown you today speaks for itself. We wanted to take you behind the scenes into the world of manufacturing. I'm Mark Tewksbury. See you next time on How It's Made. Hello everybody, I'm Mark Tewksbury, your host for this program. Our goal is to reveal the methods and materials that turn out the everyday products you see around you. If you thought you knew something about these items, you might be in for some surprises. There's a whole world of things waiting for us to discover here on How It's Made. On today's program, compact discs, cheese, pantyhose, and fluorescent tubes. Some people are drawn to those shiny cars with that special metallic finish. Metallic paint actually contains metal particles, most often aluminum. Powdered metal is combined with paint paste to provide color, brilliance, and that metallic effect. The larger the particles, the greater the effect. Millions of data bits representing numbers, words, music, and drawings, today all available on compact disc. The best part for me is it's so user-friendly. Compact discs are copies made from an original glass master disc. A thin plate of glass is first placed in this unit, which brushes the surface to perfectly clean it. The machine starts up. Cleaning is done with deionized water and a small goat hair brush. The excess water is eliminated by the rapid rotation of the disc. The disc then goes into this surface analyzer, where a laser beam inspects the cleanliness of the surface. At this stage, two chemicals are applied, a primer and a photoresistant coating. This operation is done at a temperature of 21 degrees centigrade and lasts 3 minutes. The disc is delicately retrieved from the apparatus. Then the photoresistant coating dries in an oven for 30 minutes. This developer has two spouts. One applies deionized water and the other sprays a solution to develop the data etched on the glass. The information is now engraved on the disc. The disc is placed in this metal coating equipment. The next step consists of applying a thin coating of nickel and vanadium. This electroforming process results in the master from which discs will be made. The etched glass is immersed in a chemical solution for 70 minutes. Then the plated piece is removed, thus obtaining a die. This die is sent off for finishing. It is stamped out into the desired shape. The excess material is later recuperated for recycling. Following on, the compact discs will be fabricated from this master unit. Here we clearly see the stamping out technique. The master is taken out. A technician peels off the film which protected the data etched onto the die. Following a visual inspection, the die is sent to the pressing department. The die is delicately installed in the mold, which will form compact discs. Discs are made from a very special plastic called polycarbonate. The mold is closed and liquid polycarbonate is injected into the die. It comes out as a small, hard, translucent disc. It is now ready to be metal coated so that it can be read by a compact disc reader. A robotic arm lifts the disc from the mold and places it on these supports. This metallizing process is extremely short and very simple, taking but a second. It consists of covering the plastic disc with a very thin coating of aluminum. Here we see the inside of the mold, where the aluminum coating is applied. In this facility, almost everything is automated. This allows for the production of over 100,000 compact discs per day. Protecting the surface of the disc is essential. So a coat of varnish is applied, which also allows silk screening to stick well to it. Ultraviolet lamps very quickly dry the varnish. And here in the pressing room, they apply the label. This step is also very fast since the machine prints 70 discs in 60 seconds. Once the silk screening is completed, the finished discs leave for packaging. Pizza, lasagna, sprinkled on a salad. Many people like a little cheese in their life. The story of making cheese is one involving milk, curds, and whey. Like all cheeses, mozzarella starts from milk. To assure good milk quality, the interior and exterior of tank trucks transporting milk must be washed after being emptied. A tank such as this one can carry an average of 30,000 liters of raw milk at a temperature of 3 or 4 degrees centigrade. Raw milk destined for cheese making contains 3.8% fats and 3.3% proteins. They store the milk and whey, a milk byproduct, in these immense silos, each with a capacity of 225,000 liters. This milk separator extracts surplus cream to adjust the percentage of fat according to the type of cheese to be made. Fabrication begins with this tank, which feeds the pasteurizer. Pasteurization sterilizes beverages which can easily ferment. Milk samples are drawn off to precisely determine their milk fat and protein content. Tests are carried out in this laboratory where they impose controls. These test tubes contain milk samples which will undergo microbiological analysis. Milk quality must be impeccable. This is a curdler with a 25,000 liter capacity into which milk and other essential ingredients for making mozzarella are introduced, such as the enzyme rennet that curdles the milk. This mix must be well stirred and cooked. The agitators are used to cut the whey into little lumps. This step takes about 30 minutes. The temperature of the tanks depends on the type of cheese they're making. Agitators continue stirring the milk. Once cooking is done, the whey is pumped onto tables to be drained. It stays there for about 25 minutes. The solid and the liquid are now well separated. The liquid we see draining is called lactoserum. The lactoserum will be concentrated and transformed into milk byproducts. The water has been almost entirely extracted and the cheese particles are now sufficiently dry. This large automated blade then moves cheese particles towards the next step. That is toward the molder. In the molder, the cheese is cut up before being carried to the cooker, the final processing step. It appears that this mozzarella has just the right texture. cheese finally arrives at the molder, which will give it the proper shape. Each mold has a 2.5 kilo capacity and is rectangular. Brine, a salt solution, serves to cool as well as to salt the cheese blocks. The blocks are unmolded and fall into a brine tank. Following on, the cheese blocks will remain in another brine solution for a while. They are then carried by a conveyor towards another tank, where they will be immersed for 4 to 10 hours at a temperature of 2 degrees centigrade. Sprays of brine remove the foam which forms at the surface of the tank. The 30,000 liters of milk that we saw coming in by truck at the beginning have enabled them to produce some 1,400 blocks of cheese in only 8 to 12 hours. The cheese blocks are finally vacuum packed, ready for shipment. Women appreciate that pantyhose come in a variety of colors, shears, and textures. Us guys, we appreciate them too. Maybe for different reasons. Making a nylon stocking takes only a few minutes. However, it's a complex operation that involves the knitting of 5 to 8 threads as fine as a hair. The threads, usually nylon and spandex, strong and elastic, are used. Sometimes polyester or cotton are added. The knitting machine goes into action. This one fashions a tube for sheer stockings in 90 seconds. In 3 minutes, it makes a tube for tights. Its speed is adjusted according to the product being made, varying between 750 and 1,200 revolutions per minute. Once the tube is knitted, it is sucked up and lands in a bag where it will be inspected. More than 500 machines share the work, each making a model that is specific for it. The two ends must now be joined. This automated machine assembles the two tubes together to form the pantyhose. Then a scissors cut the pantyhose, a necessary step in production of a pair. This opening is enlarged to allow for sewing, which will join the two tubes at the point of the panty. The label with the size or brand name is already sewn in place in just 10 seconds by this robotic machine. At this pace, it sews on 4,800 labels in 8 hours. Installing a gusset requires some preparation. A scissors makes a hole at the joining point. Then the stocking is turned inside out by suction so that certain stitching can be done on the inside. Thus, these stitches will be less visible. Now the foot must be sewn. This robotic machine places the foot in position. Then a sewing machine makes stitches at the same time that it cuts away excess material. This step requires only 10 seconds. Then the pantyhose is turned right side out, again using suction. Everything is ready for installation of the gusset. The pantyhose is placed in a tub and taken to this department. The stocking is again suctioned and placed on a gusset machine by the operator. This method assures that the gusset will be installed well-centered without a pleat. Putting in the gusset is the final operation in the process. A pre-cut piece of cotton is slid into the space reserved for the gusset and automatically sewn in. Only aesthetic touches remain, such as adding a little color to the pantyhose. They're placed in this machine, which has a large drum with 4 compartments and a 45 kilo capacity. The pantyhose are washed in soapy water then immersed in dye. Temperature climbs gradually to 93 degrees centigrade. After a 5-minute rinsing cycle, a softener is added. This all takes 2.5 hours. Once dried, they proceed to inspection. The pantyhose is placed onto a form which stretches it to allow inspecting for any imperfection. If all is well, the pantyhose is transferred onto another metal form where it will be pressed. The pantyhose is positioned, guided by a magic eye. The pantyhose is then carried toward a steam room, remaining there for 2.5 seconds before being dried in 7.5 seconds at 140 degrees. They fold and pack 420 pantyhose per hour and make 180,000 pairs per day. Besides providing light as cool white or with a rose-toned color, fluorescent tubing is also known as being a very low energy consumer, which is probably why we find it in so many homes, factories, and offices. Once the only source of light was the flame of fire in the forms of torch, candle, and oil lamp. It remained so right up until the 19th century, when gaslight made its first appearance around 1840. Almost 40 years later, Thomas Edison invented his famous incandescent light bulb. In 1909, the Frenchman Georges Claude developed the fluorescent tube, a light remaining unaltered to this very day. Did you know that mercury permits us to see in the dark? The production of fluorescent lamps is highly complex. The fabrication process starts with glass tubes that have been meticulously cleaned with warm water to remove dirt and impurities. Then the tubes have to be specifically shaped with a folder shaper. They're heated for 30 seconds, then quickly curved using a template. This automated machine can bend 14 tubes a minute. The bent tubes go into the coating chamber, where a thin coat of phosphorus is applied to their inner surfaces. It's phosphorus which produces light by transforming ultraviolet generated by the ionization of mercury. Then the surplus phosphorus is removed from the ends of the tube to facilitate sealing them. They now move to the electrical components. The cathode mount is made in this auto mount. Here they make the wire carrying current from the mount. The wire carrying the current is shaped. And here the wire is heated. This prepares it for the next step because it's essential to prevent the cathode coating from spreading to the prongs. The filaments are inserted into their mounts. The emissive substance plays a crucial role. When heated, it emits electrons which participate in producing light. The emissive substance is actually this liquid, and the wiring mount is transferred from the auto mount to the sealing machine. At this stage, the wiring mount and the glass tube are finally joined. Sealing is done at a very high temperature. One important step remains. This is where the glass tube is emptied of air and filled with gas. This machine also decarbonizes the tube and introduces the drop of mercury, essential for producing light. Once the very tiny drop of mercury is injected into the tube, the production process for making the fluorescent lamp is now nearing completion. But one step still remains. This threader positions the wires for insertion of the tube cap, which serves to establish electrical contact. The tube cap is placed into position in preparation for sealing. The cap must not only be securely attached, but also installed in a watertight way to eliminate any risk of leaking. The capper permanently seals the cap onto the tube, and it's all finished. Each lamp is tested on a large testing wheel to verify its quality and good functioning. And once the meticulous inspection is over, the fluorescent lamps are carried to the packaging department. A robotic machine handles the lamps and places them into the packages. The glass tubes have now become fluorescent lamps. If a picture's worth 1,000 words, I hope what you saw today speaks for itself. Our goal was to show you behind the scenes of manufacturing of everyday items. I'm Mark Tewksbury. See you next time on How It's Made. Hi, I'm Mark Tewksbury, your host of this program. Our goal is to reveal the methods and materials that turn out the products you see in your everyday life. From toothpicks to airplanes, we'll look at them all. If you think you know something about those items, you might be in for a surprise. There's a whole world of things waiting for us to discover here on How It's Made. Did you ever wonder why, when driving at night, your headlights are reflected in the yellow or white paint that marks the road? The answer is simple. That paint has tiny beads of glass in it, making the lanes more visible and driving much more safe. On today's show, copy paper, jeans, computers, and plate glass. Do you remember hearing that with the advances in technology, we'd use less paper? Ha! I seem to be using more paper than ever before. Paper production begins with the arrival of wood at the mill. Paper is made from a paste produced from a mix of 65% maple, 25% birch, and 10% poplar. They require 2 tons of wood to produce 1 ton of paste. Everything starts from this debarking drum, which removes bark from the logs. It's about a 20-minute operation. The bark will be burned to produce steam, required for the operation of the mill. The debarked logs are transported on this conveyor. All is controlled by an operator. Now the logs are reduced into small pieces called kindling. They're accumulated into a pile and remain outdoors, winter and summer. The kindling looks like this. These 5 piles total about 30,000 tons of kindling. Next step, reduce the kindling into a paste. They begin by washing it. This screen verifies that the washer is properly loaded. Then comes alkaline cooking. This diagram controls its operation. This huge cylinder is the washer in which the kindling is cooked for several hours at a temperature of 158 degrees centigrade. And this is the recuperation boiler. It burns wood lignite at 1,000 degrees. Certain chemical products which come out fused as lava are recuperated. This black liquor, a residue of burned wood, will be burned to produce steam. Exiting the washer, the brown paste is washed and sent to the thickener. With this spatula, they verify the quality of the brown paste washing. The paste must be bleached. This alkaline extraction tower places the brown paste in contact with chemical products. It's bleached with chlorine dioxide and gradually becomes more white. Then the water is partially drawn off. This worm screw breaks up the paste so it can be pumped into storage reservoirs. Water is extracted with this equipment, the Bellois Belbet 3 paper machine, operating at a speed of 1,060 meters a minute. Between the entry and the exit, the concentration of water in the paste falls from 95 to 5%. Here we see the sheet of paper coming out of the presses. Then analyzers verify the quality parameters of the paper and signal any anomaly. The paper is then rolled up. This roller produces enormous main spools. With this transfer arm, they change a full spool for an empty one. A roll weighs over 35 tons and contains 60 kilometers of paper. The spooler cuts the main spools into smaller, less wide rolls. Some will be delivered as is, while others will be shipped to paper cutters. Rolls are sent to an automated warehouse. In the warehouse, they store rolls which will be cut later. Robots, guided on rails in the floor, feed the Beelomatic paper cutter. This is the one that produces copy paper. Robots are controlled by a central computer directed by operators. Production reaches 55,000 sheets per minute. We see here the transfer section of the cutter. 4 automatic catchers and operators verify paper quality before packaging. In 1 hour, this mill produced 6,600 packages of copy paper. A single log allowed for the production of at least 15 packages of copy paper. What was once the rugged garment material for factory workers, farmers, and tradesmen is today one of the most popular clothing items in the world. Yes, jeans are a fashion statement. Jeans are made from a highly rugged cotton called denim. This enormous roll contains 450 meters of fabric, from which they will produce 350 pairs of jeans. Several thicknesses of the material are unrolled on this long table. This knife can cut up to 100 thicknesses of the material at a time. By multiplying the thicknesses, they produce a whole pile of pieces with one cut. They shape the denim pieces following cutting patterns. Each piece of the jeans has its own cutting pattern. The little pieces of fabric are cut with a clicker, also known as the stamper, which cuts out pockets with a cutting mold. Exerting 1,500 pounds of pressure, it can cut 20 pockets at a time. They begin sewing. Jeans are sewn with 100% cotton thread. This needle pierces the fabric 4,000 times a minute. Designs are embroidered on the pockets with this machine. Its needles move at 2,500 strokes per minute. And this pocket robot will simultaneously fold, press, and sew a pocket. This machine allows for the installation of 75 pockets in 60 minutes. And the pocket is now sewn into place. Next up, the buttonhole. This machine sews the contours of the buttonhole, and a steel blade comes down to cut the opening. The closing button is positioned. This machine is used to make the loops, which will hold the belt in place. The loops are sewn, as usual, with cotton thread. At this stage, they assemble the different pieces of the jeans. This operator joins the two pieces of denim at the crotch. And then she sews it. Then they sew the exterior of the leg. This sewing is done flat with an overcaster which cuts excess material proportionately and to size. Now for the zipper. This machine installs the zipper holdfast and the slide. The zipper is sewn into position. The final sewing step consists of installing the jeans belt, a strip of fabric. This operation requires only a few seconds. The jeans were made up on the reverse side so that all stitches would be on the inside when the jeans are worn. The pant is then turned right side out with this turner, which has 100-pound suction power. All that now remains is to steam press the jeans. This operation lasts only 20 seconds and eliminates any pleats. This company makes 1,500 jeans every day. Producing a pair of jeans will have taken 12 minutes and 50 seconds of work and will have required between 1.1 and 1.2 meters of fabric. Can you imagine a modern household or office without this revolutionary device? The computer? I can't. It takes about 90 minutes to assemble a computer. Its hard drive disk saves information transmitted to it for a long time. The reading head reads the information. It is extremely precise. The space between the reading head and the hard disk is as thin as a hair. The hard disk is installed in its position within the computer. There are two other units which safeguard information: the removable 3-inch disc reader and the CD-ROM reader, which allows for the reading and execution of programs recorded on compact discs. These two units are placed into position. The spinal column of the computer is the motherboard. It is to this unit that the other elements of the computer are connected. This cooler dissipates the heat generated by the chipset. Certain sound cards are integrated directly on the motherboard. These connections, in sequence, are the audio input, its output, and the microphone port. This AGP retaining ring secures the video card during transport. This thermal unit measures the temperature emitted between the processor and the motherboard. The processor is the brain of the system. It interprets, calculates, and executes the instructions given to it. The processor has several millions of transistors, and its cadence, its operating speed, reaches the gigahertz level. The processor rests on this base. The processor's cooler dissipates the intense heat. Its efficiency depends on the type of material used, and a conducting material assures better cooling. The RAM memory stores short-term information, but erases it when the current is turned off. This memory is more rapid than that of the hard disk or the CD-ROM. Now they integrate everything in the case. It protects the internal elements from the external elements. At this stage, they install the electronic components in this case. Several connectors of the case are connected to the motherboard, such as the commutator and various light indicators. This is the output connection for the video card, which links the computer to the monitor. We also see the video chip, which creates images in 2 and 3 dimensions. Here is the video memory. The more its capacity is increased, the clearer will be the image displayed on the monitor. The video card is placed into its position. The modem allows 2 computers to communicate. Its condensers produce the perfectly clean phone signal to facilitate communications. These modem chip connectors control information circulating between the 2 computers. The fax modem is installed. The power supply transforms electricity according to the voltage required by the different components. The computer's interior cabling is installed. It allows information to travel between the different media and the motherboard. The IDE cable is connected and the CD-ROM. The last electrical wires are connected to different computer components. The assembly of 30 components of the computer is now finished. Just before closing the case, they test each computer to verify the good functioning of the peripherals. Then they close up and proceed to packaging. This company produces about 300 computer units every day. So clear, so perfectly flat, absolutely huge. But let's make it very clear. Manufacturing plate glass is anything but simple. We can speak of the use of glass since the time of the Egyptians 4,000 years ago. It wasn't used in construction, though, but merely to enclose small objects. Later, the Romans became masters of glassmaking, with their methods being used up until the 18th century. By the end of the 19th century, glass was no longer just a luxury item, but became a construction material as common as steel and concrete. Plate glass is made from several raw materials mixed with a little water. These materials are silica sand, soda ash, dolomite, limestone, nepheline syenite, and salt cake. It begins by dumping into a hopper pieces of recycled glass together with the raw materials. It will all be melted. In a continuous stream, the mixed materials go into a gas-fed furnace. Temperature inside the furnace is 1,500 degrees centigrade. It contains 1,500 tons of molten glass. They use 500 tons of it every day. In this regenerating chamber, combustion air is preheated to 1,000 degrees. The materials of the mix begin fusing, and the molten glass is stirred up. The homogenizer mixes the glass to equalize its temperature. Pouring will be done within several hours. In the glass industry, they call this machine the top roller. The glass is poured onto a bath of liquid tin on which it floats. As soft as toffee, it's molded into a ribbon. All equipment in the tin bath is cooled with water so that it won't break from the heat. Coming out of the bath, the glass is at 600 degrees. The glass must again be cooled, and this unit is used to do that. This huge ribbon of glass is 3.3 meters in width. the ribbon of glass rolls gently on rollers, gradually cooling along the way. The glass is still soft. The marks we see are imprints made by the top roller. The glass must have a uniform thickness. This laser scanner measures its thickness to within 1/100th of a millimeter. The glass is now fairly hard. They proceed to cutting it. This ultra-hard tungsten carbide roller makes a longitudinal score before the glass can be cut. Now they proceed with transverse scoring, made according to the dimensions customers have asked for. The scored glass separates easily. The glass strips are separated and continue along on the conveyor. These roller breakers cut the edges of the glass sheet. Leftover pieces fall to the ground and into a chute. They will later be recycled. These rubber-covered rollers convey the glass sheets to the inspection department. When they arrive for inspection, these immense glass sheets are handled with great care and are positioned upright. The glass is inspected for faults with fluorescent lamps. Once inspected, the glass sheets are handled one at a time and stored vertically. Making the glass took several days of work. It is now ready for delivery. Heat fusion has transformed solid ingredients into transparent glass. If a picture's worth 1,000 words, I hope what you saw today speaks for itself. Our goal was to give you a view of the many manufacturing methods that produce the things we see in our daily lives. I'm Mark Tewksbury.